In the realm of deep neural networks, a significant vulnerability has been identified in the form of well-crafted perturbations that can easily compromise model performance. Top-K multilabel learning, TKML, a widely applied approach in multimedia tasks such as information retrieval and recommendation systems, is particularly susceptible. To address this, the concept of measure imperceptibility is proposed, aiming to generate adversarial perturbations that deceive visual perception and evade monitoring of measures like precision at K. And to achieve this, a novel loss function is devised, and an efficient algorithm with a convex objective is established to optimize this objective. Extensive experiments on large-scale benchmark datasets, including PASCAL VOC 2012, MS COCO, and NUS WIDE, demonstrate the proposed method's effectiveness. In the realm of adversarial multilabel learning, a critical concept has emerged that has been neglected in previous studies: measure imperceptibility. This paper introduces and explores this novel idea, proposing a new imperceptible attack method for top multilabel classification problems. The author's proposed method is designed to satisfy both visual and measure imperceptibility, making it a significant advancement in the field. To demonstrate the effectiveness of their proposed method, the authors conducted experiments on large-scale benchmark datasets, including PASCAL VOC 2012, MS COCO 2014, and NUS WIDE. These datasets provide an extensive platform for testing the robustness and efficiency of the proposed attack method. The paper highlights the importance of measure imperceptibility as a critical component of adversarial multilabel learning. It emphasizes that previous studies have focused primarily on visual imperceptibility, neglecting the importance of measure imperceptibility. By introducing this concept, the authors aim to bridge the gap between visual and measure imperceptibility, enhancing our understanding of adversarial attacks in multilabel classification tasks. The proposed method leverages the concept of measure imperceptibility to create a more sophisticated attack strategy. This strategy not only ensures that the attack is visually imperceptible but also measure imperceptible, making it difficult for current detection methods to identify the attack. The experiments conducted by the authors show promising results, demonstrating the effectiveness of their proposed method across various datasets. This suggests that the proposed method could potentially outperform existing attack methods in terms of both visual and measure imperceptibility. In conclusion, this paper presents a groundbreaking approach to adversarial multilabel learning by introducing the concept of measure imperceptibility. The proposed method demonstrates a significant advancement in the field, offering a more comprehensive understanding of adversarial attacks and their implications for multilabel classification tasks. In the realm of top multilabel learning, imperceptible adversarial perturbations pose a significant threat. This is particularly concerning in untargeted attacks where the goal is to manipulate the model's predictions without being detected. A crucial aspect often overlooked in existing research is the invisibility of these perturbations for measures, which can have profound implications on model performance and security. To address this gap, we propose a novel attack method that replaces relevant categories in the top set with several irrelevant labels. This approach draws inspiration from works on image-specific perturbations and multilabel adversarial learning, aiming to deceive common multilabel metrics such as precision, recall, and F1 score. The optimization of top ranking is also a critical component of our proposed algorithm. Specifically, we utilize the average top loss, ATK, as a surrogate loss function to guide the optimization process. By minimizing ATK, we can effectively manipulate the model's predictions to include irrelevant labels within the top set, while ensuring that the perturbations remain imperceptible. Our method leverages the inherent vulnerabilities of multilabel classification models, particularly those that rely on ranking-based metrics for evaluation. By exploiting these weaknesses, we can create powerful adversarial attacks that significantly degrade model performance, highlighting the need for more robust evaluation methods and defense strategies against such threats. Average of top K optimization is a valuable tool in constructing objectives for various tasks such as information retrieval and recommendation systems. It entails minimizing the predicted score for the relevant category to be higher than the K+1 th largest score. To address the non-differentiable ranking operator issue, The authors propose a series of surrogate loss functions, including the sum of ranked range and average top class. They also introduce the concept of measure imperceptible attack, which aims to attack a few categories while not degrading the performance of ranking measures. The optimization problem involves minimizing the perturbation norm while ensuring specific categories are ranked lower than the KTH position and other relevant categories are ranked higher. The authors then relax the optimization problem by leveraging the Lagrangian equation and a lemma to form a convex optimization framework. This framework is designed to reduce the loss generated by combining the maximum score of specified labels and the KTH largest score, along with the perturbation norm. The paper introduces a novel approach to generating imperceptible perturbations in top multilabel learning, referred to as top K measure imperceptible attack, TKMIA. This method modifies the original optimization problem by introducing a new objective function that averages the top optimization. The proposed algorithm, TKMIA, iteratively updates the perturbation and the corresponding variables using the gradients of the new objective function. It can be applied with two different selection schemes, global selection and random selection. The paper outlines the experimental settings, including datasets like PASCAL VOC 2012, MS COCO 2014, and NUS WIDE, and evaluation metrics such as multilabel top K accuracy, precision at K, average precision at K, and normalized discounted cumulative gain at K. These metrics demonstrate the effectiveness of TKMIA in manipulating the ranking of labels without altering the visual content of the image. The presented table highlights the average performance of various methods under different K values, focusing on metrics such as accuracy, precision, mean average precision, MAP, and normalized discounted cumulative gain, NDCG. The results demonstrate the effectiveness of the proposed method, T_KMIA, RS, in achieving better performance across all metrics compared to existing methods like T_KMLAPU, _KFool, and MLCWU. The perturbation algorithm's success is measured through metrics like average attack effectiveness, delta L, and average perturbation, APER, showcasing its efficiency in modifying the top relevant labels while maintaining the overall ranking performance. The TKMIA method, designed for generating imperceptible adversarial perturbations in top multilabel learning tasks, is implemented using PyTorch with ResNet 50 and ResNet 101 as backbones on VOC, COCO, and NUS datasets, respectively. The attack period involves normalizing images into the range of 1, 1, and utilizing SGD as an optimizer. Well-trained victim models are selected to ensure the effectiveness of the attack under various specified categories. Results analysis, presented in tables 1 and 2 for COCO and NUS datasets, reveals that TMIA outperforms other comparison methods in most cases, achieving smaller changes in metrics while perturbing more specified categories. A visual comparison of attack methods on NUS datasets demonstrates the superior performance of TMIA. While competitors can remove specified classes from top predictions, they often raise the scores of irrelevant categories, leading to performance degradation. In contrast, TMIA perturbs specified labels and increases the scores of relevant categories, resulting in a more effective attack that confuses metrics. The proposed method, TKMIA, is a novel adversarial perturbation technique designed for top multilabel classification models. It aims to achieve both visual and measure imperceptibility, making it more effective at evading detection by defenders. This is achieved through a simple and convex objective function, which is optimized using a gradient iterative algorithm. In the experiments, TKMIA outperforms other baseline methods in terms of visual imperceptibility and measure imperceptibility under both global and random selection schemes on various datasets such as NUS, COCO, and VOC. The results are presented in Table 3 and Table 4, with Figure 2 and Figure 3 providing visualizations of the top 3 and top 5 successful performance comparisons under global and random selection schemes, respectively, on NUS dataset. These findings demonstrate that TKMIA can generate perturbations that are less noticeable while still causing significant changes in the model's predictions. Furthermore, TKMIA strikes a balance between visual imperceptibility and measure imperceptibility, leading to better overall performance on delta L and APER metrics. This paper concludes by summarizing the effectiveness of the proposed method and its potential applications in enhancing the security of multilabel classification models. The research was supported by several grants from the National Key R&D Program of China, National Natural Science Foundation of China, and other institutions. When measures are unreliable, imperceptible adversarial perturbations can significantly impact top multilabel learning. This concept is explored in the context of multimodal learning algorithms and network architectures for information extraction and retrieval. The study discusses the importance of robustness against adversarial attacks, highlighting the need for efficient top-rank optimization with gradient boosting for supervised anomaly detection. It also emphasizes the role of universal adversarial perturbations in challenging the robustness of deep neural networks. The research draws upon various techniques, including frequency-tuned universal adversarial attacks on texture recognition and geometry-inspired top adversarial perturbations. The findings underscore the importance of developing robust models capable of withstanding such perturbations to ensure reliable performance in real-world applications. Researchers have made significant strides in machine learning, artificial intelligence, and computer vision, with a particular emphasis on developing adversarial attacks and defenses, as well as multilabel learning and image recognition techniques. Adversarial attacks, which involve intentionally perturbing input data to mislead machine learning models, have been shown to be highly effective against state-of-the-art models. In response, researchers have developed various defense mechanisms, including techniques for detecting and mitigating these attacks. In the realm of multilabel learning, researchers have explored methods for assigning multiple labels to a single instance, such as in image classification tasks where an image can belong to multiple categories. This has led to the development of novel algorithms and architectures that can efficiently handle complex label relationships. Image recognition techniques have also seen significant advancements, with the rise of deep learning-based approaches that can learn robust feature representations from large datasets. These techniques have achieved state-of-the-art performance in various image recognition benchmarks, demonstrating their effectiveness in real-world applications. The paper provides a comprehensive review of these research areas, highlighting key challenges, opportunities, and future directions. It also discusses the importance of developing more robust and reliable machine learning models that can withstand adversarial attacks and generalize well to new, unseen data. Furthermore, the paper emphasizes the need for more research on multilabel learning and image recognition, particularly in the context of real-world applications where data is often noisy, imbalanced, and scarce. In top multilabel learning, imperceptible adversarial perturbations pose a significant threat to model performance. To contextualize this issue, we examine the performance of well-trained models on various data The table presents the results of competitors and the proposed method, TKMIA, on the task of imperceptible adversarial perturbations toward top multilabel learning. Under different K values and globally selected SUN NUS, the metrics delta TK-AC, delta map at K, delta NDCG at K, delta L, and APER are used to evaluate performance. The table highlights TKMIA's superiority over competitors, including animals 2mLCWU, K-FOOL, and TKMLAPU. TKMIA achieves the best performance in most cases, with smaller differences between original and perturbed metric values. For instance, in the animals dataset with K equals 2, TKMIA has a delta TK-AC of 0.2410, outperforming animals 2mLCWU and K-FOOL. Similarly, in the landscape dataset with K equals 2, TKMIA achieves a delta TK-AC of 0.1300, outperforming landscape 2mLCWU and K-FOOL. The results also showed TKMIA's performance improves as K increases, outperforming in the traffic dataset with K equals 5. Overall, the results demonstrate the effectiveness of TKMIA in generating imperceptible adversarial perturbations for top multilabel learning. Figures 4, 5, and 6 present the top successful performance comparisons under different selection schemes on the VOC and COCO datasets. In Figure 4, the top 2 successful performances are depicted under the global selection scheme on VOC, with a maximum iteration of 300. To enhance contrast and visibility, all perturbation intensities are magnified by a factor of 100. The specified labels, relevant labels, and irrelevant labels are marked with dark green, light green, and red, respectively. Figure 5 illustrates the top 3 successful performances under the random selection scheme on VOC, with the same maximum iteration and perturbation intensity magnification as Figure 4. The label markings follow the same convention as Figure 4. Figure 6 displays the top 5 successful performances under the global selection scheme on COCO, again with a maximum iteration of 300 and perturbation intensity magnification by a factor of 100. The label markings are consistent with Figures 4 and 5. These figures provide a visual representation of the performance comparisons under different selection schemes and datasets, allowing for a direct evaluation of the proposed method's effectiveness. The magnification of perturbation intensities enables a clearer visualization of the results, facilitating a more accurate assessment of the method's performance. These results build upon the previous discussions on the selection schemes and their impact on the performance of the proposed method. The comparison of the global and random selection schemes on VOC and COCO datasets provides valuable insights into the robustness and generalizability of the method across different datasets and selection strategies. In a comprehensive evaluation, we benchmark our method, TKMIA, against competitors across various datasets, including vehicles, animals, household, and person, under different K values. The results, presented in the table, demonstrate significant improvements in accuracy, precision, and other metrics for our method, particularly when faced with imperceptible adversarial perturbations. Notably, our method outperforms competitors in these challenging scenarios, with the best results under each set of parameters highlighted in bold. The superiority of TKMIA is evident in its ability to maintain robust performance even when K values vary, showcasing its adaptability and effectiveness in real-world applications. The authors present a comprehensive evaluation of their proposed method, TKMIA, alongside competing approaches, 2mLCWU, K-FOOL, and TKMLAPU, on the VOC dataset under varying settings of K and randomly selected set sizes. S performance is measured using 5 metrics: delta TK-AC, delta map at K, delta NDCG at K, delta L, and APER. Lower values indicate better performance for the first 3 metrics, while higher values are preferred for the latter 2. Results are displayed in tables 16 and 17, with maximum iteration set to 100 and 300, respectively, and delta equals 2. Across different K values and set sizes, TKMIA consistently outperforms competing methods, achieving the lowest delta TK-AC and delta map at K values in most cases. Notably, TKMIA achieves the best results when K equals 2 and S equals 2, with delta tk ac equals 0.3043, delta map at k equals 0.2246, and delta ndcg at k equals 0.2028. Figure 7 visualizes the top 5 successful performance comparisons under the random selection scheme on the COCO dataset, with the maximum iteration set to 300. Perturbation intensities are magnified by a factor of 100 to enhance contrast and visibility. The figure highlights Qianqian's superior performance, with dark green indicating specified labels, light green indicating relevant labels, and red indicating irrelevant labels. In top multilabel learning, evaluating the reliability of measurements is crucial. A comparative analysis of various methods under different conditions reveals the superiority of the proposed method, TKMIA. The evaluation involves varying values of K and sizes of randomly selected sets S, with metrics including delta Tk ac, delta L, and APER. These metrics quantify the difference between original and perturbed values, with smaller values indicating better reliability. The results show that TKMIA consistently outperforms other algorithms across different settings, achieving lower delta Tk ac, higher delta L, and lower APER. This indicates better reliability against imperceptible adversarial perturbations. The performance of TKMIA remains superior even as the size of set S increases or decreases, demonstrating its robustness. The findings underscore the importance of considering imperceptible adversarial perturbations when developing machine learning models, particularly in applications where reliability is paramount. The proposed method, TKMIA, effectively enhances the reliability of top multilabel learning in the presence of such perturbations, making it a valuable contribution to the field. Comparative results of various methods on COCO are presented, focusing on performance metrics under different K values and sizes of randomly selected set S, with maximum iterations set to 300 and 500. The table highlights the disparities in accuracy, precision, mean average precision, MAP, normalized discounted cumulative gain, NDCG, and average precision, APER, among the methods. Notably, the impact of varying K values and the size of set S on performance metrics is showcased. The best results under each set of parameters are bolded, revealing a range of performances across the methods. In the realm of top multilabel learning, a comparative analysis is conducted to evaluate the proposed method, TKMIA, against its competitors, MLCWU and TKMLAPU. The NUS dataset serves as the foundation for this evaluation, with varying settings of K and randomly selected S sizes. Performance metrics for each method are presented in tables 21 and 22, including delta Tk ac, delta L, and APER. The delta symbol denotes the difference between original and perturbed metric values, where smaller values indicate better performance for delta Tk ac and APER, and larger values are preferable for delta L. Table 21 presents results with a maximum iteration of 100 and a perturbation radius of 2. Consistently, TKMIA outperforms its competitors across all metrics and settings, demonstrating its effectiveness in generating imperceptible adversarial perturbations for top multilabel learning. Table 22 showcases results with a maximum iteration of 300 and a perturbation radius of 2, further highlighting Qianqian's superior performance in creating robust and efficient imperceptible perturbations that significantly impact model predictions without perceptibly altering the original data. These findings collectively suggest that TKMIA is a potent tool for crafting imperceptible adversarial perturbations in top multilabel learning tasks, providing valuable insights into the vulnerabilities of deep neural networks in this context. The table presents a comprehensive comparison of the proposed method, TKMIA, with competitors under varying parameters. For each set of parameters, the results are evaluated across several metrics including accuracy, precision, mean average precision, and normalized discounted cumulative gain. The proposed method, TKMIA, demonstrates a trade-off between these metrics, showcasing its adaptability and effectiveness in different scenarios. Notably, TKMIA outperforms competitors in terms of precision and mean average precision at K equals 3, indicating its strength in selecting relevant features. The results also highlight the impact of K on the performance metrics, suggesting that the optimal value of K depends on the specific application and desired outcome. Overall, the table provides a detailed analysis of the proposed method's performance and its position within the competitive landscape.